This is the chapter, this is the review for our third exam. And so I wanted to take just a second and walk through just a couple of things about the exam itself, just to help us get ready for it. And then I'll open it up and we'll answer questions and kind of take it from there. So first of all, 22 total questions, not 18. But 22 total questions on the exam. Most of them are multiple choice. One thing that you will notice as you go through kind of the material here, there's no math. This is not, there's no need for a calculator for this exam. Everything here is conceptual. The split here is about 50, 25, 25. The majority of the material coming from Chapter 4, because Chapter 4 was kind of like the baseline. We built everything in Chapter 5 and Chapter 6 off of Chapter 4. And so anything that we did with Chapter 5 kind of spoke to Chapter 4 as well. That's why it seems to be so Chapter 4 heavy. But if you look in here, one thing that is missing from the Chapter 4 topics here is nomenclature. So even though the practice exam did have some nomenclature questions on it, the exam on Wednesday will not have nomenclature questions on it. Like I said last week, I already tested you on that material, and I don't see a need to keep hammering that home. You've got the proficiencies to do that for you. So while we can go over those nomenclature questions if you wish, and I did mark correct answers on the practice test from those, understand that it will not be something that you see on Wednesday. Chapter 4 material focuses mainly on bonding, on that concept of lattice energy, which most of you did pretty well with in the Chapter 4 quiz, on the covalent bonding and Lewis structures, on bond length and strength and the relationship between them, on electronegativity and bond polarity, determining what bond is polar, what bond is not, how polar they are relative to each other. In Chapter 5, we're talking about VSEPR theory, hybridization, polarity, valence bond theory. So all these kind of going in together. Can you look at a Lewis structure and give some basic information about the structure itself? What is its molecular shape? What are its bond angles? Is it polar? Can we look at a bonding structure and determine how many sigma bonds, how many of those direct overlap interactions there are versus how many parallel interactions there are? Can we look at the structure at the steric number and determine hybridization? And then out of Chapter 6, identifying the different types of intermolecular forces and where we see each of them, using those intermolecular forces to explain different kinds of physical properties. Getting into what solubility is a little bit deeper. What a solute is, what a solvent is, how the solute and solvent interact with each other. We've kind of dipped into that more as we've been talking about Chapter 11 here. But this is, again, more of a theoretical discussion. And then reading, interpreting phase diagrams. Now, for materials, as far as what you get in preparation, I'm going to go back to Chapter 5 here for a second. Oh, if I had it here. material that you're going to get that'll help you, you're going to get this exact table, the same thing that you got for the Chapter 5 quiz that has the summary of the 3 most complicated shapes in terms of their geometries and how all that ties into hybridization. That all will be given to you along with the periodic table and our normal equation sheet. The only thing that is listed here that is not given to you is this table of electronegativity values. And that's mainly because you're just not going to need to know them that deeply. So that is the exam. That's what we're going to be doing on Wednesday. So turn it over to you now. What are some questions that you have that I can try to answer, try to help clarify some things for you as you're studying and preparing? Go ahead.
Number 1 on the free response section.
Okay. All right, so number 1 in this free response section says, we have 2 resonance structures for the thiocyanate ion shown. Question is one of these favored over the other, and which one would be favored? Justify the answer. So we can look at this and we can make some preliminary evaluations. We can look at this and say, okay, SCN minus, I should have 6 plus 4 plus 5 for the nitrogen and an extra for the charge. That's 16 electrons. Okay, do both of these structures have 16 electrons in them? Well, 2, 4, 6, 8, 10, 12, oh, let me count it. 2, 4, 6, 8, 10, 12, 14, 16 on the left. 2, 4, 6, 8, 10, 12, 14, 16 on the right. So both structures are at least valid on their face. Let's look at formal charge. For the nitrogen over here, 5 valence electrons minus 3 bonds and 2 dots gives me 0 formal charge on this nitrogen. Carbon, 4 valence electrons, 4 bonds, no dots. Formal charge is 0 on the carbon. Sulfur, 6 valence electrons, 1 bond, 6 dots. There's where my -1 charge. So I've got a -1 charge on this sulfur in the structure on the left. If I look at the opposite side, nitrogen, 5 valence, 2 bonds, 4 dots. Here's a -1. Carbon, 4 bonds, no dots, no charge on the carbon. Sulfur, 2 bonds, 4 dots, no charge on the sulfur. So remember, when we were evaluating structures in Chapter 4, and we had a situation like this, this isn't quite the same thing as resonance. Resonance would imply that there is an ambiguous nature to the decision. I could go to the left, I could go to the right, it wouldn't make a difference. Well, in this case, it does make a difference. I'm getting a formal charge on a sulfur versus a formal charge on a nitrogen. And the two are not the same. They have different electronegativities. What I have to point out here, though, is that, again, if I'm looking at just does it meet the minimum criteria, I've got the correct number of electrons, I've minimized formal charge. That's about as good as I can do without getting into the nitty-gritty here. Unfortunately, this question asks us about the nitty-gritty. It's asking us to choose between the two. How do I choose between the two? Well, this is where that electronegativity scale comes in. Which element is better suited to have that -1 charge? The sulfur or the nitrogen? And if I look at the electronegativities, I see that sulfur has an electronegativity of 2.5. Nitrogen has an electronegativity of 3.0. The nitrogen is more suited toward that negative charge than the sulfur is. And so as a result, this structure on the right is the more favorable structure. Both structures are good. And in fact, that electronegativity difference is not significant enough. We're not going to be talking about like the structure on the right is 99% of all of the thiocyanates and the one over here on the left is 1%. It's probably more like a 3-to-1 mix. Or maybe even getting closer to 50-50. They're not that far apart from each other. So chances are pretty good both are going to exist. Which one exists just happens to, which one shows itself happens to depend on what it's reacting to, what its environment is. So in terms of choice, we would choose this one here on the right. What would we say about it? Well, we would talk about the negative formal charge is on the more electronegative atom. And that would be the primary reason why that one would be favored as opposed to the other. Now, if we roll it back, and we're talking about things from the standpoint of, let's say I asked you to draw the thiocyanate ion for one of the exam questions, and you drew the one on the left instead of the one on the right. Would I mark you wrong? Yes. But we're talking about a partial credit deduction and a relatively small one, as opposed to a flat out 0 out of 3 or whatever the value of the question would be. Because the one on the left is valid. And if you draw a valid structure, you're going to get the majority of the points associated with the question. Now, if there happens to be a better structure available, yes, I'm looking for the best structure always. But if you draw a valid one and it just happens not to be the best one, that's okay. Again, you're going to get the majority of the points. Any questions here?
So would we be able, or should we be able to tell which one is more eliminated without the sheet?
So yes, usually. Like I said, this one we gave you the table because that was a question that was going to feature it prominently. If there were something like that without the table, then we would be looking at a group by group or a row by row kind of comparison, comparing nitrogen to oxygen, comparing chlorine to bromine or something along those lines. The general rule of thumb is electronegativity depends upon charge and size. So you may look at the two of them and say, okay, well, they're both equal distance from fluorine. They're both 2 squares away if you don't go diagonally. Why is the nitrogen more favored? It's smaller. So that charge density is higher, which is going to favor electronegativity. All right, another question. Okay, so just as a reminder, this is a phase diagram. And so phase diagrams are basically graphs. On the one axis, you're going to have pressure. On the other axis, you're going to have temperature. Now, the regions of the phase diagram are always going to be consistent. The big zone where we have high temperatures and low pressures, this will always be your gas phase region. Up here where the pressure is high and the temperature is cold, this is always going to be your solid region. Here in the middle, this will always be your liquid region. So the other points of emphasis here really come from interpretation. And largely what phase diagrams are all about is graphical analysis. So what we can look at is, okay, we can clearly see A is in the solid region. So if we had a question about A, we know that A is in the solid region. It is a solid at that temperature and pressure. We know that B is a gas. We know that C and D are on the boundary lines between. Now, the question always is, if I'm looking at something on a boundary line, how many boundaries is that line actually representing? And so if I were on a boundary here just between solid and liquid, then we would call that boundary either freezing or melting, depending upon what direction we were going. If I were looking at the boundary between letter C and letter D, we would be talking about boiling or condensing. If I were talking about the line between D and the bottom of the graph, we'd be talking about sublimation or deposition, depending upon, again, which direction we were going over that line, left to right or right to left. But these points in the middle, D and C, are actually special points in and of themselves. If you look at D, you can see D is at the interface of all 3 phases. It is directly on the boundary between solid and liquid, and solid and gas, and liquid and gas. For that reason, letter D is referred to as the triple point. That is where all 3 phases of matter exist at the same time. Notice also that after C, see how the pressure line flattens out here? It's no longer climbing, 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 it goes flat. Well, that's because C isn't just an ordinary point, it's actually something called the critical point. And we talked about this at the time with chapter 6. The critical point would represent that point, that temperature and pressure condition, where we could no longer tell the difference between gas and liquid. So that's why the line flattens out. Because at this critical pressure, that is the last pressure that we can tell the difference between the two. After that, it kind of goes into what we call a supercritical fluid. So the question is, or at least question 14 is, if I begin at point B and steadily decrease that pressure, what am I going to, or excuse me, decrease the temperature, what am I going to see happen? Well, if I draw a straight line from B and decrease the temperature as I go, what I'm going to see is that I started in the gas phase and it managed to go from the gas phase to the liquid phase, grab a cup of coffee, and then go from the liquid phase to the solid phase after that. What do we call those transitions? Well, going from gas to liquid is called condensation, and from liquid to solid is called freezing. So we're talking about letter E here. For number 15, it's referencing C here. C is the critical point. So if you look at the key that I posted, C could technically represent a boiling point. Since it is at the critical juncture, you could also make a pretty strong argument that it is none of those because it is in fact the critical point, and at that temperature and pressure condition, we don't see the difference between the two anymore. So on this exam, I accepted both answers. We were looking for A, but E has a pretty strong argument for it as well. So we accepted both as a for that reason. The last question, if you began at point A, what should you do to make gaseous ammonia? So again, this is where we have to take into consideration what our substances are. This was a liquid, this was a gas, this was a solid. If we are at point A here, we have a couple of options. One option would be to simply increase the temperature. And yes, it would go through the liquid phase first, but it would eventually all become gas. So that's one option. Another option would be to go the other way. Lower the pressure, bring it back down to atmospheric pressure from where it was, and you could turn the solid into gas by sublimation. Both are viable options. Now, there's a third option. You could do both at the same time. Raise the temperature while lowering the pressure. But in terms of what's being asked, what your options are, decreasing the pressure, that's one of them. Increasing the temperature, that's another. Answer is F. You could do A or C. You could actually do both A and C. Now, if the question were more specific in terms of, say it was, how can you turn the substance into gaseous ammonia without undergoing a phase change to the liquid? Then decreasing the pressure would have been the only way to do it. Because it's pretty clear to see that if you increase the temperature at all, there's a good chance you're going to end up going through the liquid phase or the triple point to get there. But aside from that, yeah. The question here was extremely non-specific intentionally, but understand that we could make it more specific if we wanted to. Right. Who has another question? Number 2, the free response. All right. Okay. For this question, what you have to do is you have to evaluate each molecule individually and then how they'll interact with each other. So for problems like this, I usually try to pick molecules that you know pretty well, or that you can rationalize pretty quickly what they are so that you don't have to draw all of them. So, for example, letter A, we've worked with ammonia and water enough that you should recognize probably close to immediately that both of these are polar and they both have hydrogen bonding. Now, if you need to prove that to yourself, you can draw them. There's the Lewis structure for ammonia. There's the Lewis structure for water. And you can see in both cases, we have asymmetry in the form of those lone pairs on the tetrahedral shape, which are going to, at the very least, initiate a conversation of polarity. Remember, for hydrogen bonding, you need to have something that is polar, and you have to have an NH, OH, or FH bond. Well, in this case, we know that we have polar molecules here. We also have an NH bond in ammonia and an OH bond in the water. So both of these exhibit hydrogen bonding as well. So they're both highly polar substances. So what kinds of intermolecular forces exist between them? Well, pretty much all of them, the exception of ion dipole. Everything has London dispersion forces. So if a question asks us to identify all of the forces that are there, London dispersion forces is always a correct answer because they're in everything. Now, if it asks us for the primary or for the strongest, then London dispersion forces are only the correct answer if the molecules are nonpolar. But in this case, we're asked to identify all, so it's London dispersion forces. Since it is polar, we also have dipole-dipole forces in play. And since we have hydrogen bonding also, hydrogen bonding will play in as well. So that identifies the first part of the question. Second part of the question, will the two substances dissolve in each other? Answer there is yes. How do we know if two substances are going to dissolve in one another? What is the guiding principle that allows us to determine one way or another? Like dissolves like. What does that mean, Sam? Right, and if I have polar and nonpolar at the same time, they're not alike. They won't dissolve with each other. So again, it comes back to, do you understand what forces exist in each one individually? If you understand the forces that exist in each one, then you can quickly determine whether or not they're going to dissolve in one another based on, do they have the same kind of forces? Now, that's not to mean that hydrogen bonding substances will only dissolve with hydrogen bonding substances. They'll dissolve in anything that's polar. Remember that hydrogen bonding is just an extreme form of polarity. Like dissolves like. Unlike does not dissolve like. And so that's pretty much what you have to do for each of these. Now, in the case of carbon monoxide, this is a heteronuclear bond. There's only one bond in the entire molecule. Is that bond polar? Yeah, it is. So if the bond is polar, it's a polar molecule as well. Now, does carbon monoxide exhibit hydrogen bonding? No, it's missing that second bullet point. It is polar, but there's no nitrogen to hydrogen, oxygen to hydrogen, or fluorine to hydrogen bond. So it's just polar. H2S. Well, kind of similar to water. We can see steric number of 4, 2 lone pairs. This is going to be a polar molecule because of the asymmetry in that those lone pairs. Does it exhibit hydrogen bonding? Has hydrogen in it, but sulfur's not electronegative enough. So that is where it will stop. So again, I can look, polar, to answer the second question, does it dissolve? Absolutely. Explanation, like dissolves like. As far as the intermolecular forces are concerned, we're going to have London dispersion forces because, again, they exist in everything. And we're also going to have dipole-dipole because of the fact that we've got polar molecules interacting with each other. But that's where we'll stop. All right, any questions with these two? All right, let's keep moving then. All right, methane and silane, CH4 and SiH4. Structures for these are simple. We've got methane and silane. All symmetrical tetrahedral molecules. So both of these are nonpolar. So again, we can answer that question of dissolving. Does it dissolve? Yes. Like dissolves like. They're both nonpolar. They'll dissolve in each other. Introduce a water molecule into this. Yeah, the water's not going to dissolve in it. But they'll dissolve in each other. What kind of intermolecular forces exist here? Well, we've got the London dispersion forces, because we always have that. Do we have anything else? No. London forces would be the only thing that we have here. And the reason why? It's nonpolar. There are no other dipoles. We're only getting that randomization showing out there.
So where would ion dipole come in?
We're about to talk about it. Okay, potassium chloride with water. So with potassium chloride, we have to recognize that this is an ionic compound. We've got potassium ions, we've got chloride ions in that sample. And in water, we've got a polar molecule that exhibits hydrogen bonding because of the electronegativity of that OH bond. Will these two substances dissolve in each other? Yes, they will. Don't get yourself fooled by the fact that we didn't write the word polar here. Remember what polarity is. Polarity is the partiality of charge inside of a molecule. Well, what is an ionic compound? Instead of a partial charge, it's a complete charge. So I've got charged particles interacting with other charged particles. That's like dissolves like. Ionic is just an extreme where instead of a partial positive and a partial negative, it's completely positive and completely negative. If this didn't happen, water wouldn't be considered the universal solvent. Salts have to be able to dissolve in water. We know that they dissolve in water. Ionic compounds are salts. So yes, these two will dissolve in each other. What kind of intermolecular forces exist between them? Well, pretty much everything. I've got the London forces, I've got the dipole forces, I got the hydrogen bonding, and now because I have an ion and a polar molecule, this is where we would have an ion dipole force as well. So like the name implies, ion dipole forces are going to be interactions between ions and polar substances. So the ionic substance provides the ion, the polar substance provides the dipole, the interaction of the two creates the ion dipole force. And yes, those other lower forces would still exist because they're showing off the polarity that would still exist in the molecule itself. And so even though that ion dipole force massively supersedes all those other forces put together, they're still present. All right, the last one, methane and ammonia. We've got complete symmetry in the methane here. So this is a non-polar substance. The lone pair in the ammonia is going to create that element of asymmetrical movement that is going to create a polar molecule here. We also have hydrogen bonding inside of this molecule because of those NH bonds inside of the polar framework. Will these two dissolve in each other? No. This is an application where light does not dissolve light. Polar substances and nonpolar substances do not interact, do not dissolve in one another. Now, what kind of intermolecular forces are going to exist here? Well, we're definitely going to have the London dispersion forces, because again, even if they don't interact with each other in terms of mixing, they will have those London forces between them. The reason they don't mix is because the ammonia would have to drop down from hydrogen bonding to London forces to mix. So it's going from very strong interactions with itself to very poor interactions with its solvent. That's unlikely to happen. The only other thing that we could possibly have here is an induced dipole. Now, if you left this off of your paper, I wouldn't have held it against you. That isn't something I was looking for. We only briefly mentioned it in passing. There were a couple of people when I did give this exam that did put that in there. I threw them a bonus point because that demonstrated some thinking that wasn't anticipated but was absolutely correct. You know, we talked about induced dipoles, especially when it came to things like oxygen dissolving in water, where that hydrogen bonding caused the bend in the molecule to allow it to dissolve in small quantities. Would an induced dipole be possible? Yeah. Is it necessarily going to happen? No. But if you made that argument, I would have given you credit for that level of thinking, because that is technically good reasoning. So on a question like that, if it happened to be there, that's what you really need to do. Break it down into its pieces and do some comparisons. If they are the same kinds of things, then we know that it dissolves. If they are different kinds of things, we know that it will not dissolve. And as far as the identifying the intermolecular forces are concerned, you just pick up the ones that are there. So basically, you go to where they are even with each other, and you stop there, whatever that is. So in this case, all it was London dispersion. In this case, ion dipole was possible because we had both conditions present.
What about the hydrogen bonds? Why are they there since potassium chloride doesn't come?
Because the hydrogen bonding would be, think about what those spheres of hydration that we talked about when water dissolves an ionic compound. That interaction is a hydrogen bonding interaction between the ion and the water molecule. If I had a different polar molecule, I would still see interactions from a dipole standpoint, but I wouldn't have the hydrogen bonding standpoint there as well. So hydrogen bonding is there because that is a specific aspect of water. And so when water dissolves something, if there's a way for those hydrogen bonds to be involved, we're going to see them. Even if we have something that isn't normally capable of hydrogen bonding on its own. So I think in some of the homework examples, it gave an example of something like acetone or some sort of organic material that had oxygen in it, but not an OH bond. And when that substance came into contact with water, the hydrogen bonding in the water forced hydrogen bonding onto the other one as well. So it is possible if the parameters are there, but you have to have them there to do that. Otherwise, we just go down to dipole. So like water and hydrogen sulfide, for example, you're not going to see hydrogen bonding between those two molecules and each other because the sulfur atom isn't capable of hydrogen bonding. So the only interactions you'll see there are dipoles and London forces because the sulfur has no capability for hydrogen bonding. All right, another question.
Will Ionic dissolve with nonpolar also?
No. No, again, think of ionic compounds as being extremely polar. So salts aren't going to dissolve in nonpolar substances, but they will dissolve in polar substances if the circumstances are correct. If we have something that's polar enough to stabilize them, they'll dissolve pretty well.
Are we going to be drawing fluid structures at all?
Yes. Yes. So a question like number 4 here is within the realm of possibilities where you have to draw something and then break it down, kind of similar to what you did in the Chapter 5 quiz. And so, yeah, molecule drawing is going to be a part of this exam.
So is the center atom always least electronegative?
Ordinarily, yes. I know in the quiz you got kind of stung by, there's a scenario where you had oxygen as a center atom instead of, and the reason for that came down to formal charge. With having the oxygen in the middle, all the formal charges ended up 0. You couldn't do that with a chlorine in the middle, at least not as easily. But ordinarily, yes. That one was kind of, that one was an unfortunate exception. Right. Okay, so number 12 is asking kind of the same thing that we were just talking about. what happens to an ionic compound when it dissolves in water? And so what we need to know happens is that, first of all, if it's going to dissolve, we know that the crystal itself is going to start breaking apart from itself. So after stirring for 10 minutes, if this is something that is going to dissolve, and we would hope sodium chloride dissolves pretty well in water, we're going to see it break away from its crystalline kind of state. Now, letter C would be closer to accurate if instead of stirring it for 10 minutes, we had let it just sit for that 10 minutes of time. We would see that slowly the water would start picking off some of those ions and separating them out. So what it really comes down to is, again, what happens to those ions once they're put into the solution? Do they just merely separate from the bigger crystal and make smaller ones, like in letter B? Do they completely dissociate and they just kind of mix themselves into the water without really interacting with it, like in letter D? Or is water a key component of that dissolving, and the water actually surrounds each one of those ions, like in letter E? And the answer here is E. So this is one of the reasons why water is able to dissolve ionic compounds and break that lattice energy of those crystals, because what we start to see is the formation of hydrogen bonds through the interactions of these water molecules and the ions as they are separating out. And so we can see they're oriented very precisely. The negative ion is attracting the positive side of the water molecule. The positive ion is attracting the negative side of the water molecule. So not only are we getting separation of the ions from the large crystal, those water molecules are actively interacting with the ions as they break off and stabilizing them. There's a high level of attraction that is existing between the water molecules and the ions themselves. And the net result is that the total intermolecular force actually exceeds the ionic attraction of the ions themselves. That's why it dissolves. If we didn't have that, then the ionic crystal wouldn't break apart. We wouldn't see that solubility. And that is largely where we get our idea of solubility rules. Why is it that some substances dissolve in water and others don't? Well, it comes down to the attractions. The ones that don't dissolve in water are more attracted to themselves than what water is able to do when it breaks it apart from the crystal. And that's what leads to sulfates usually being soluble, except for in this situation, and carbonates almost always being insoluble, except in these little tiny situations. That's where the solubility rules ultimately come in. So E is your correct answer here. Other questions? Got about another half hour of time if we need it. We good? Four? Multiple choice? Okay. All right. This is one where having that table side by side with you is going to help you a lot. Which of the following would we expect to be flat? Molecule that with a central atom that has 4 bonds and 2 lone pairs, 4 bonds and 1 lone pair, 5 bonds and no lone pairs. All of them were the first 2. So if we go down to this table here, what we were asked to look at were these scenarios. 4 bonds, 2 lone pairs, 4 bonds, 1 lone pair, 5 bonds, no lone pairs. Now, in order for something to be flat, that means it can't have any 3-dimensionality to it. It has to be planar, 2-dimensional. Well, so right off the bat, the one with 4 bonds and 2 lone pairs fits that description. Square planar is going to be flat because square planar is going to have all 4 of those bonds in that equatorial plane and the 2 lone pairs in those axial positions, top and bottom. So those 4 bonds, they're all in the same 2-dimensional space. By definition, that's flat. Now for the others, we're looking at trigonal bipyramidal and seesaw. Well, we have to remind ourselves of what trigonal bipyramidal looks like. Trigonal bipyramidal means I've got a center atom here. So on its face, this is going to be pretty hard to be 2-dimensional. And knowing how we have to orient those lone pairs to each other, it's going to be really hard. Really, the only one that is 2-dimensional is the linear shape when we have 3 sets of lone pairs here in this plane. Everything else is going to have some level of 3-dimensionality to it. I mean, maybe T-shaped. I have my lone pairs here. Yeah, we can call that one flat. That's not one of the options. We didn't say anything about 3 bonds, 2 lone pairs. It's either 5 bonds and no lone pairs, so the true trigonal bipyramidal, which is definitely 3-dimensional. We've got the flat region and the axial region. And then seesaw, kind of the same thing. Yeah, one of those positions is taken up by a lone pair. So if I take that one off, I still can see that I've got one 2-dimensional plane here and one 2-dimensional plane going back and forth. That's a 3-dimensional molecule as well. So the only one that fits the description is the square planar one. 4 bonds, 2 lone pairs. So that would be A. This one gives us square planar. This one gives us seesaw. This one gives us trigonal bipyramidal. And neither of those two are anything close to two-dimensional. Even though they have two-dimensional planes in them, the whole molecule is not two-dimensional. Square planar is. Oh, yeah, and I realized now I messed that up on the key. So I'll add that one after the fact. So for the nitrite ion, you would have, this would be NO2 -1. So 5 for the nitrogen, 6 for each oxygen, and an extra 1 gives us 18. So the Lewis structure would end up looking something like this. It would have a resonance structure, but you're not asked to put the resonance in. And as far as the VSEPR theory is concerned, the resonance would not make a difference. What you would recognize, however, though, is that on this nitrogen, we have a steric number of 3, 1 for the lone pair, 1 for each of the sets of bonds to oxygen. So from that domain geometry, you have trigonal planar. The lone pair is going to turn that trigonal planar into bent, which is going to squeeze the bond angle down to less than 120. Hybridization for steric number 3 is sp2. And I should recognize I have 2 sigma bonds, 1 to each oxygen, and 1 pi bond, resulting in that double bond. So I will add this to the key. It'll be out of order because, again, when I did this, the students did the exact same thing that I did. They skipped letter A because they thought it looked like instructions. And so I was quickly making this key this afternoon. I did the exact same thing. I just kind of skimmed it. So yeah, if you look at the key, it's going to have A, B, C, D, xenon, and so on. I'll put the nitrite ion as letter E, just so that it's there as well. But that's what you would have to do. All right, any other questions? Hope.
Number 11, multiple choice.
Sure. All right, number 11 asks, which of these are capable of hydrogen bonding? Remember the criteria for hydrogen bonding. It has to be polar. And it has to contain one of those special bonds to hydrogen. And so, really, even if you didn't know that some of these are polar and some of them are not, just based on this definition, none of them have this kind of bonding other than letter A. There's no oxygen, nitrogen, or fluorine in any of the molecules other than the first. So from a logical standpoint, there could only be one correct answer here, unless there's no correct answer. And we know that water is capable of hydrogen bonding. We know how polar water is. We've talked about it endlessly for the past month or so. Of these other ones, the methane's not even polar. Letter C is polar, but it has no hydrogen bonds. Letter D is nonpolar. Letter E is nonpolar. So there's only one other polar option there, and it didn't have hydrogen bonding either. Number 7. The strongest intermolecular forces that occur between CH3Cl molecules arise from, okay, some of these answers are junk. We never said a word about disulfide linkages. Don't even consider it. Yes, they do exist. No, it has no application here. First of all, you have to have sulfur, and there's no sulfur in the molecule. So what we have to look at is we might have to actually draw this molecule out to see what it has. And if we do that, we can see that we're going to get a tetrahedral here. That tetrahedral is going to have one atom different than the others, so it is polar. So since it is polar, we can strike London dispersion forces. They are there, but they're not going to be the strongest because it's a polar molecule. For ion dipole interactions, you have to have an ion. There's nothing ionic here. Already talked about disulfide linkages being a junk answer. Hydrogen bonding. We don't have the right kind of bond here. You'd have to have either an HF and NF or an OF, or I'm sorry, HF, NH, or OH, and we have none of those. So since it's polar, we knew we had dipole-dipole forces. It's just a matter of, did we have anything else there? And in this case, the answer is no. All right, what's the answer to number 8? Today. Yeah, we talked about it today. The reason it's on this is that it was in that physical properties mini lecture that I had you do as part of your post-lecture assignment. But we just talked about it today, so I kind of seen who was paying attention. So yeah, when vapor pressure and atmospheric pressure are equal, that's when we define a liquid as boiling as opposed to just simply evaporating. And so that is the relationship that exists, and how we can have a relationship between the vapor pressure of a gas or of a liquid and the boiling point of that liquid. We know that if the vapor pressure goes down, the boiling point is going to be higher, just because the two are related that way. But at a lower vapor pressure, there's a lot more energy to get to atmospheric pressure than if I'm already at, if atmospheric pressure is 760 millimeters, but I've got one liquid that's at 500 and another one's at 200, the one at 500 is going to have a lot less energy to gain to get up to 760 than the one at 200. You're talking about a gap of 260 versus 560 millimeters of mercury. And that relates directly to intermolecular forces. The reason the one at 200 is because the forces holding it together are stronger than the one that's at 500. All right, any last questions? Sounds like we're winding down. All right, so just as a reminder, tomorrow you are taking the Chapter 6 quiz in lab, so I will get a chance to see you in lab tomorrow. So if anything does come up between now and then, feel free to just ask me when you see me. You know that you can get a hold of me through Remind or email or any of a number of other ways as well. So if something comes up and you needed an answer, just shoot me a quick text. I'll be happy to get back to you. Thanks for coming today, though, and I'll see you on Wednesday.